Okay, another hour and a half. Good. So to continue with the talk on onion routing. Okay, so some basic characteristics of onion routing and the Tor network. So it's an overlay network. It runs over TCP. Data is sent in fixed sized cells, Tor cells. The client computer, so the network is composed of a network of servers and then some software in the onion computer, and the client computer, which has installed what is called the onion proxy. The first thing that this proxy is going to do is to fetch from the directory servers the list of descriptors of the Tor server so that it knows where to contact the Tor nodes and how to create connections through them. Users select the routers that constitute the anonymous channel. When we say users, we mean the onion proxy, right? It's not like the user manually selects anything. But this is what is called source router, in the sense that the initiator of the communication determines the full path of the communication all the way to the destination. And this is in opposition to other anonymous communication services, such as crowds, that use what is called random routing. In random routing, the path is decided at every step. So in random routing, I would send, in crowds, for example, I would send my request to another node, and that node would decide, where to send it next, either to the destination or maybe to another node in the network. But I do not have full control over the path in the network. In onion routing, you do, because you do this sort of nested encryption. In order for this nested encryption to work, you need to know which keys to use, because nobody else except for the people with the right keys can decrypt or should be able to decrypt the communication. And Tor not only provides anonymity for the clients, it also can be used to provide anonymity for servers. And this is what is called the hidden servers. These are some of the most controversial parts of one of the most controversial features of the Tor network, because it has been used for conducting activities that are illegal in most places, if not all places. So yeah, in all places actually. So there was the Silk Road you might know about. This was like a big drug market that was operating as a hidden server in Tor. It was taken down by the FBI. I'm not sure if there's a new Silk Road emerging again or not. Took about 10 months, but they're up and running again? 2 months. 2 months. Well, different people, I guess, because the guy is in jail, right? Well, we don't know. They're anonymous. Obviously. Sorry. And there was also Freedom Hosting, what's even worse in a way, because it was hosting lots of child pornography, actually. And it was also taken down by the FBI. They were able to. It's unclear how they did it. Some of the news reports said they use like financial information on payments and sort of detective work. Other people suspect that they might have gotten help from the NSA, that then they do these parallel reconstruction stories in which they create a plausible story of how they got to the same information without using, I don't know, the information from the optic fiber cables or whatever information they were using. Anyway, those are sort of the controversial, illegal services that are to some extent inevitable if you're running a system that provides these kind of protections, but there are also many good uses for hidden services. And just to give you a couple of examples, one is anonymous or pseudonymous blogs. So it seems that some people, specifically I think in this case from Iran, they were running blogs that were critical of their government, and the system was consistently being denial of service. Okay, so they moved to run it as a Tor hidden server, and because in a Tor hidden server you cannot really see where the service is being hosted, it becomes a lot more difficult to deploy a denial of service attack against it. So that's a nice hidden server to have. And some newspapers, like the New Yorker, is running also a hidden server which is called Strongbox, and this is for anonymous leaks and anonymous tips for people to be able to get in touch with the newspaper without revealing their identity and be able to maybe give information that they don't want to give in their own name. This is also another nice use. So this is the reason why, I mean, the fact that there are users that are sort of desirable, generally speaking, or at least for the people who make the decision on whether to still have this feature enabled, it is nice to have the possibility to have these services. Okay, so just a graphical illustration of how Tor works. We have a bunch of onion routers. We have a user Alice, and Alice wants to anonymously serve some news sites. Okay, so the first thing that she has to do is to contact the directory servers and download the public onion keys. So the keys that allow her to talk to all these onion routers. That's the first thing. Then once she has gained knowledge of which routers are available in the network, she selects 3 of them to construct a connection. Okay. She has the keys for these routers that she obtained from the directory server. So she first contacts the first router, R1, and she does an authenticated Diffie-Hellman exchange in which only the server is authenticated. She remains anonymous, but she wants to know that she's talking to the real Tor server. So she establishes a tunnel to that server, a connection to that server. And then inside of that connection, she tells the R1 extend the circuit to R2. Okay? So then she repeats the process of doing a handshake with R2 inside the connection, embedded in the connection with R1. This means that basically R1 receives like the blue communication, strips out the blue link of encryption, and then forwards the rest to R2. The process is repeating in R2, in which R2 is told, please extend the connection to R3. And again, now things are going to be encrypted. I mean, after these connections have been established, Alice has session keys that are shared with R1 and R2 and R3. So everything is encrypted there. And each of the routers is stripping out one layer of encryption. And then the actual communication that she wants to route is going embedded in the innermost layer of this communication. Only R3 can see which is the end destination. So here only R1 knows that Alice is the initiator of the communication. Only R3 knows what the destination of the communication is. But R1 cannot see the destination, and R3 cannot see Alice, and R2 can only see that something is going from R1 to R2. This is a very simplified, it's actually much more complicated than this in the sense that, for example, there are guard nodes, so R1 is not randomly chosen, but instead Alice usually will have a set of 3 routers that she uses as first hop, and there are reasons for this. The reason is that, I think I get to back later, if not you can ask, I believe it's later in the slides. But the guard nodes were introduced to prevent certain attacks. Also, the network is complicated in the sense that not all nodes are exit nodes, so not all nodes act like R3. Why? Because there are many people who do not want to run an exit node and then be seen as the initiator of connections, because if something happens over that connection, then you appear as the initiator, you will get in trouble. Even if you have ways of saying, well, it wasn't really me, then maybe you need to have a lawyer, maybe you have paperwork to deal with. So for example, in our university, we're running a Tor node, but we are not an exit node because the university administration was sort of freaking out with the possibility that something could happen and then they would get into trouble, and so we don't have an exit node. We only route connections within the Tor network. So this is only a subset are actually exit nodes. Yeah, I think this is the main sort of idea. Also, the routing algorithm is not just you select randomly 3 uniformly. It's much more complicated than that. It's weighted by bandwidth, because the nodes are very diverse. Some nodes have lots of bandwidth, some nodes are very small. So you need to do some load balancing in the network. That means that nodes that are bigger should be chosen by more people. nodes that are smaller by less people, so the selection algorithm is biased towards bigger nodes compared to smaller nodes. Also, there are constraints that you do not choose once you have chosen a node, for example, R1, you do not choose a node R2 that is within the same, or you only choose one node within the same /systing IP subnet. Okay, why? Because since in onion routing you do not delay messages. This is actually the next slide. But since you do not delay messages, it's not so difficult to correlate inputs and outputs, and therefore you want to have distribution geographically and in terms of jurisdiction, and in terms of ISPs, and in terms of autonomous systems, and in terms of internet exchanges, so that you do not get the same entity being able to see input and output, because they might be able to correlate. So this is getting into the next thing, which is end-to-end correlation. So end-to-end correlation can be passive or active. The problem, so the issue with Tor is that unlike the mixes that we saw in the first part that do shuffling and do delaying and really make it very hard to correlate, here, because you have high volume traffic, if you were to delay, you would have a very significant impact on usability. So this is the first problem. Okay. The second problem is that you have people are accessing diverse resources, which are, let's stick just to websites. Every website is very different from every other website in terms of the traffic pattern that it generates, in terms of the size, the number of resources included in the website, and all of these things. Okay. So that means that you have a big variability between the traffic of one connection and the traffic of the other connection, also in terms of a start and end of the communication, all kinds of things. So basically, if you're able to, so if you observe one onion routing and you would have just one input stream and one output stream, which is bidirectional, counting packets would be enough to basically match input and output. Counting or even if you can do it end to end, so you are able to observe Alice here, you can see nothing of here, but you can also observe Bob at the other end, then you're able to see that the traffic leaving Alice looks very much like the traffic getting to Bob, and vice versa, and that with a very high likelihood this is actually the connection between the two endpoints. So packet counting is one way of doing it. Looking at inter-packet delays is another way of doing it. Start and end of streams. These are just some examples of things you can use to correlate streams. You can also do it with active attacks. So if you are, imagine you are the website and you also can see Alice here. So you might be able to inject a pattern of like, first I send you like a big file, then I stop for 2.5 seconds, then I send you another big file, and you inject a pattern that is very easy to recognize. And then you recognize it at the other end, and then you have also de-anonymized the connection. You have even higher confidence because you have more control over, you can inject patterns that are more unusual somehow, so that you can reduce the false positives with respect to doing a purely passive attack. And you might have heard, there was, I think in the news, not so long ago, there was this, I think it was a Black Hat talk that was cancelled, and there were like all these, suspicions of what had happened, and then the Tor network said that there had been an attack on the live Tor network, and they sort of identified, and there is, I'm not sure if this has been confirmed, but there is this rumors, or I don't know how to call it, that maybe this is connected, that the attack that the researchers were implementing, they did that on the live Tor network, and that this is the attack that the Tor network actually identified. By the way, if you want to do research on Tor, don't do it like that. Okay, I mean, they have actually nice guidelines on how you can do research without putting in danger actual users, which is what happened in this case. You de-anonymize your own connections, and very often you can just use emulators like Shadow or Experimenter in order to do a lot of the testing. So anyway, the attack was it's an attack that used a new feature. It's called the relay early attack. So these are some control cells that were introduced in the protocol to prevent people from creating paths that would be like extremely long, and that could be used for denial of service, for overloading the network. So I can create a Tor path that goes through every Tor node multiple times, and then I send like a little bit of traffic there, and it just bounces around everywhere. So with very few resources, I'm able to bring down the network or to overload the network very easily. So they introduced this relay early attack, which was some control cells that would make sure that the paths were not too long, right? So what these researchers did, but the relay early is usually sent like downstream. So it's usually the guard node sending these cells towards the exit. In this case, what they did was use these control messages from the exit towards the guard. So what they did was that the exit node, the last node, would somehow look at the destination and would encode the name of the destination in the relay early cells, okay, with some coding, and then send that back to the guard node. So the guard node would, if the guard node belongs to the attackers, then the guard node can see these control cells coming that encode, you know, because they are not really used even in that direction, that encode the name of the destination. The guard node knows, so the guard node is the first node, knows the user, and now it has gotten the destination. You have broken the anonymity of the communication. It's a new way of attacking the system, but it's not a new attack in the sense that Tor is not protecting you against, in any case, against adversaries that control both exit and entry, because of this reason, because you can count packets, you can do all kinds of things. So in that sense, it's not like a new threat. It's just a new way of exploiting this capability of having both entry and exit. So guard nodes are a countermeasure to some extent to end-to-end correlation. Okay. There's different reasons to introduce guard nodes. One is that if you are choosing different nodes every time, it would be relatively easy for the adversary to insert a few malicious nodes in the network and enumerate a large number of clients, right? Because you would be picked every time by new clients, so you would be able to enumerate lots of clients. So guard nodes are basically forcing you to use always the same entry point, or it's basically a set of 3, and they are rotated not very often, like every few months, and they're even considering extending that period even longer. So it has a curious threat model thinking behind this guard node. It goes a little bit in the direction of saying, okay, you probably go back to the same websites again, over and over again. So it's a bit the disclosure, so the persistent behavior issue. If your guard node is malicious, then you're screwed, okay? Because it will see everything. If your guard node is honest, then you're going to be fine, because you will not be in a situation in which your connection has a malicious first node. Now, compared to the situation in which you randomly choose every time, let's suppose that I use Tor to go to, just to simplify, to go to one website, okay? If I choose different nodes every time, at some point, with some probability, even if the adversary has a small fraction of the nodes, I will be in a situation in which I have chosen malicious entry and malicious exit. So with these two, the adversary is able to de-anonymize my connection. The threat model here is thinking de-anonymizing one connection is as bad as de-anonymizing many connections. Why? Because first of all, it could be that you are repeating your visits to the same websites. Therefore, the anonymizing ones that you are the guy who's publishing on this blog is as bad as doing it 100 times. I don't gain much more from observing you doing the same again. And yeah, so this is a little bit the threat model, which is a bit unusual because it somehow makes a strong assumption on user behavior and on sensitivity. Yes?
Do you know who actually runs the guard nodes? Do you know who runs all those 4,000 or so?
For some cases you do. So anybody can run a Tor node, anybody. And actually the Tor project, I guess there are individuals there that run nodes, but the Tor project does not run the Tor network. They provide the software and the directory servers. But the Tor nodes are run by volunteers, and anybody can run them. For some of them, you don't know who they are. That's, if you want to have an open network that is easy for people to join, you run that risk. For others, it is well known. For example, the Chaos Computer Club, they run a few servers. Many universities run a few servers. And for those, you can advertise, okay, this, Tor node is run by this institution. But for others...
We don't expect that the nodes be run by the government
block it.
Correlate traffic.
They want to provide service.
Yeah.
So they provide a service so they use it and then they can tell who you are.
Yeah. So they do run some, I mean, the slides, the Snowden slides, it seems that they are running some. GCHQ and NSA, they said they had some Tor nodes running, but it doesn't seem to be a very large number, at least according to the slide, but to be honest, we don't know. Some people say that it might be safer for them to actually compromise the computers that are running the Tor nodes by other people rather than running it themselves, because that might provide them with some exposure, maybe. But we don't know, really. I mean, that's part of that's why you choose several, and yeah.
The fact that you have Tor nodes that anybody can create Tor nodes and anybody can create traffic does make it extremely hard to defend against the denial of service attack, because you can do it not only from the outside, which is probably not all that hard, but also from the inside. So you have to design the system to defend against denial of service attack by Tor nodes, right?
I don't think Tor is very resistant to denial of service. Like if you want to DOS Tor, I think that's probably something that can be done with moderate resources. Yeah. I mean, moderate, you need to have some bandwidth to do it, but it's not so large that it's really hard. I mean, what they were trying to, this idea of introducing guard nodes to make it a little bit more difficult is that it shouldn't be possible, for somebody with very little bandwidth to just, DOS the whole thing, but creating like loops that go around. But if you have lots of resources, like a nation state could easily block it.
And you can also, but because you could have 50 or 100 Tor nodes yourself for lots of them.
Yeah.
Then you can also attack it from the
sure,
inside. Right?
Sure. But you can also do it from the outside. I'm not sure if the inside gives you much advantage for DOS. It does for other things, but yeah. Oh, disconnect. Okay. Okay, I go on. So there was one attack on Tor. Tor does not aim to, as I said, so Tor does not aim to prevent this attack because preventing this attack is simply too hard. So it's an open research problem. How to do this in a way that is, cheap and reasonable and still usable is not, we don't know how to do this. But there's a variant, it's not a variant, it's a different attack, it's called website fingerprinting that has a much weaker threat model. And this would be desirable to actually protect against this attack. So here, the adversary does not control both ends. Okay? It only can see locally the user. So the adversary here could be my ISP, could be somebody who can sniff my Wi-Fi connection. It could be really almost anyone who's in proximity of me. Okay, so this is a much weaker threat, and Tor should be strong enough to protect against it. So, but the strategy of the adversary here is that it would somehow make a database of website templates. Okay. So as adversary, if I want to know if you're going to Facebook, for example, what I would do is connect to Facebook through Tor many times, make some sort of template of how the traffic that comes back looks like in terms of volume, in terms of traffic shape, and all of that, and then observe your communication. And if I see a pattern that looks like one of the patterns in my database, then I know which website you're visiting. Okay? So yeah. Okay. So it's template matching, but instead of live with the two ends, you only have one end, and the other part of the matching you have done yourself in advance by downloading many times. So there are many attacks in the literature on website fingerprinting. There was even a paper, I think it was in Oakland recently, looking at defenses against website fingerprinting that have been proposed, saying we cannot defend against this, all the defenses fail. So there has been this discussion ongoing about whether how effective is website fingerprinting, can we defend against it, is it impossible, all of this. So we actually have a recent work that will appear in CCS next CCS in October, looking at the previous work in website fingerprinting and looking at some of the assumptions that are made commonly in these papers. And we think that maybe in practice is not so terrible, like website fingerprinting, not so devastating. Why? So a lot of these experiments are made in a closed world, meaning that there's a universe of whatever, 20 websites or 100 websites. In practice, if you do not have a very good idea of where the user might go, you have an open world, and therefore you might have, you know, by the base rate fallacy, you might have, you know, a very large, a much larger number of false positives that are, you know, induced by the fact that you had a model with these 100 websites, but the user is not going to any of those, is going to other websites that are not in your database, and you still think that they are going to one of those. There are other experimental issues, such as using very clean traces. This means that the user is only downloading one website at a time in the experimental setups, so no tab browsing, which we can think that, you know, people in general, I mean, it's not uncommon to do tab browsing, first of all, and if you're using Tor, it's probably a little bit more common because it's a bit slower, so you might have more of a tendency of opening multiple tabs at the same time. Not only the tabs, but also starting and ending of a page load. So maybe it's not so. So in the experiments, they start page load, end the page load, you know, and the researcher knows exactly what the first and the last packet is, and they use this, you know, when they are matching it to the classifier, when they are using the classifier to decide which website you're going to. They know this. In practice, it might not be so easy to know that a page has been completely downloaded now and a new page is coming, even if you're not using tabs. And then there are all kinds of assumptions regarding replicability of the adversarial setup when they are downloading all these sites to make the sort of the training, the database of templates, and that is trained on these traces, and the actual setup of the user. So what happens if the user is using a different Tor browser version? Well, does the traffic change or not? Well, it does change a little bit. What about personalization? Because maybe the website, maybe, you know, these websites have different, look different for you and for me, especially in Tor, where, you know, the exit nodes might be in different countries. You might have localization of pages, meaning that, you know, when the adversary made the training, the exit was in Germany, but then when the user is using Tor, the exit is in the US, and the page actually looks different because it's the website is personalizing it according to where the request comes from, which in this case is from the exit node, wherever it is. Yeah. And what about data becoming stale? So if I am the adversary, I make the database of templates right now. Is it still valid next week? If this is for BBC News, probably the website looks rather different, even after 1 or 2 hours. So some websites are highly dynamic. So to what extent, you know, depending on the websites that we choose, we might have very different results of actually succeeding in the matching. So how to defend against website replicability? Because this is something that Tor really should be defending against. I mean, it's a local adversary, so there is no excuse, right? So currently, I mean, there is research ongoing on looking into dummy traffic strategies to defend against dummy traffic, against website fingerprinting. On the one hand, web traffic is too diverse, so it's very difficult to make 2 pages look the same or to make 2 pages to be confusable with each other. But on the other hand, you know, given all the previous issues that I mentioned of, you know, traces not being clean in practice, and all these factors that are not really under the control of the adversary, it might be easier than we think, that adding some dummy traffic might actually, in practice, help you go a long way towards making these attacks very difficult. Okay. So you can also attack Tor without observing the network edges. So this is an attack in which the adversary controls a website and a Tor node, okay? And cannot observe the network at any other point. So the idea here is that the target connects to my website, okay? And then I want to guess the sequence of Tor relays that the client is using. So I already know the exit because it's the one connected to my website. I want to then find the middle node. So for that, what I do is that from my corrupt Tor node, I send traffic over the Tor relay, okay? And then the website destination sends the the user a big file. Okay? So this big file is going to somehow make the Tor relay be very busy, and that means that the measurement traffic I'm sending through this relay 2 is going to be affected by the queues induced by the other file. So basically, because they are sharing a resource, if you increase the volume of one of the connections, the other connection is going to suffer in terms of latency. And then if I see that there is a correlation between my changes in my measurement traffic and the bursts that I send from the website, I can somehow infer that this node is part of the path. If there is no correlation, then it is not part of the path. Okay. So that helps you find the 3 nodes. You still didn't find the client. This is how it would look like, right? Like the moment I'm saying bursts, the latency increases. So if it's correlated, I mean, after a few of these bursts, you would have high confidence that you guessed right. Once you have that, you have the 3 nodes in the path, then you can use additional techniques to find the location of the Tor client. So you construct a circuit over the same 3 nodes, and then you can start measuring difference in RTT, and then do some triangulation to find where this client might be located. Okay. There are many other attacks on Tor, civil attacks. So this is what was mentioned before, introducing lots of malicious nodes in the network. And actually, I think in the NSA slides, it was mentioned, like maybe we should just introduce a bit more, some more. There are browser and device fingerprinting that was we also spoke about before with one of the questions, which is distinguishing clients by differences in their browser or on the device, for example, through the fonts they have installed. And this is very active area of research to really try to prevent these attacks from being possible in Tor. There is a big issue with secure downloads of the Tor software, because if I can trick you into downloading Tor software that is not good, then you don't have the descriptors of the real Tor nodes. You only have the descriptors of the nodes I tell you about, and then you're connecting to me, and then I have everything. Okay. The thing is that if you want to especially if you want to have people connect to your own nodes, you would need to actually tamper with these downloads. Because so the way to find which are the addresses and keys of the Tor routers is you get that from the directory servers. Okay, these are 8 servers. They have a consensus, what is called a Tor consensus. That is a list, signed list that they all sign, saying, okay, these are the Tor nodes that are active right now. Now you have to the trust is transferred to these directory servers. If 4 of them are honest, you would still get the correct list. And the Tor software actually has hard-coded in it the addresses and keys of these directory servers, precisely to prevent cases in which you might trick the Tor software to connect it to other ones. But still, you have the issue that if I intercept your download and I give you a fake client, then everything breaks. Denial of service, I mean, is definitely possible. And there have been some problems, like with the Heartbleed, I think it was. There was also some issues affecting Tor. Also, when there was this what was the name? DigiNoter case, they had fake certificates for several services, and Tor was one of them, actually. So, I mean, of course, there are dependencies with other security building blocks, like SSL, that if there are problems with those, then, this will also be affected. So Tor is used for having anonymous communications, but actually it has a dual function. And I would say that as important as the anonymity service is the censorship sync convention that was, we also spoke a little bit about already. So part of the idea, the relationship between the two is that if I don't want you to go to a certain website, but I don't, then I can block that site. But if you're connecting through Tor and I'm not able to determine to which website you're going, then obviously I cannot block you, right? So that's the anonymity helps you with achieving censorship circumvention. So you can either block Tor as a whole if you want to block some sites, and this is done in some countries. I've heard like the Belgian police telling me that they would like Tor to be blocked in Belgium. I don't know if they want to join that list of countries there. Maybe they do. But I mean, there are issues. It's not so easy to do that, to get that ban passed, fortunately. You can also block the directory authorities. That would be a very cheap way to block Tor, because you just block eight IP addresses, and then people cannot get keys or descriptors. You can block all relays, or you can try to identify the handshake and then block the connections, the TLS connections. So solutions, the bridges I already mentioned, flash process, and then on top of that, a steganography of the protocol, so that it's not possible to identify from sort of the headers in the TLS handshake. Some people have proposed other systems such as Skype morph, so disguising connections to Tor as connections in Skype. And then another system is like Telex, which is like using ISPs, as I said, that use this some random nonsense in order to encrypt some information that then allows them to identify that something is a Tor connection. Okay, conclusions, coming to the end. So traffic analysis is very easy and cheap to extract information, and there are many inferences that you can make from it. It is difficult to defend against, and we have to do all this, routing and bouncing around the world, and still the security that you get is rather limited. And yeah, it affects electronic communications in general. When you are dealing with traffic analysis resistant systems, you want to define very clearly which properties are you trying to achieve. Are you want to provide anonymity, or you want to provide an observability, or you want to provide, some degree of unlinkability. With respect to high latency systems, they are very secure, and they have very nice, well understood security properties, although there are a couple of attacks that they are vulnerable to, but the functionality is limited, because tolerating high latency, I think we are used to having things very fast and immediate, so it's not so nice to have to wait for things for being delayed. Low latency systems are very popular and usable, but the security is conditional to, or is limited in many ways, in the sense that there are a number of attacks that can be deployed and that would identify you. So this is it for anonymous communications. Can I take like a 3-minute break before going to the other one? Okay, thank you. Thanks. I don't know if you have any questions about this before we move on to the next topic. No? Okay. Yeah, question there.
Maybe both for availability and vulnerability, are there any thoughts regarding making the routes dynamic, like alternative routes or something like that?
Making the routes dynamic, what do you mean?
Like the user selects a few alternative routes, for example, instead of a single one.
I believe Tor creates already more than one path. Not so much for denial of service reasons, but for random failure reasons or congestion. So if one path starts not performing very well, you already have others open, and you don't need to wait for all the tunnel establishment to happen before you can switch. I believe that is the case already. Context switch. So I'm going to talk about obfuscation now. Yeah.
I have a question. I've been seeing many researchers lately that many of the researchers are working on Tor system darknet. I also know the I2P darknet, but I can't see any significant researchers about it.
Yeah.
The question is it more secure, and this is why there is less, or is it not interesting enough? So this is why.
So I think the answer to your question is not just technical. So Tor, I think, was created by people who were very active in the research community, and therefore I think it was easier for them to engage other researchers into looking at their system. And they have been very active as well in encouraging people to look at their security, to find attacks, to find fixes, They have students, you know, having internships, working for Tor. So they are, I think, very integrated with the research community, doing anonymity in that respect. Also, the people who started Tor, like Roger Dingell and so on, they were people that were very active. So I think this is sort of a sociological reason why, you know, Tor is such a, you know, it's attracting so much attention from researchers. I think Tor was also designed based, like, learning all the lessons that were, I mean, well, it's based on onion routing, which is an early design, and it is also because the people who work on it are very deep into research and very connected to research. They take all the research that is coming out very seriously, and they are very engaged into evolving their system, you know, to, you know, within what is possible without hurting too much performance or usability, into having all these countermeasures. I2P, and the design decisions are really based on what do we know, you know, from the academic literature. I think I2P was, I mean, I don't know much about I2P. It was designed a little bit from scratch. I am not sure to what extent they took into account a lot of lessons learned of attacks that exist for other systems. One of my students actually published a paper before he became my student in 2 or 3 years ago with some attacks on I2P, and they were like rather simple attacks. So I would think that, I mean, it's very unfortunate for I2P that it's not getting more attention, because that would be a way for them to, you know, for everyone to know to what extent it might be vulnerable to attacks and how to fix them. I am not sure the design is also interesting enough in the sense that of being very challenging for people to engage with it. I am not sure to what extent I2P has the extensive documentation that Tor has that makes it easy for people to figure out what is going on and to make, you know, sound experiments. Like this student of mine, he basically had to sort of reverse engineer in a way how I2P works, because it was not like there was like this, you know, really good specification saying how it works and justifying design decisions and all of that. So that's, I'm saying this without knowing much about I2P, because I don't think, yeah, I haven't seen much about it, I mean, as you say. Yeah, I haven't looked into it myself either, so yeah, thanks. Any other thing before we go into this? Okay. So let's talk about obfuscation now. So to be honest, I mean, it's not so much of a change of topic, because trying to protect against traffic analysis is a form of obfuscation as well. So it is actually a little bit related, even if we give things different names. So I have 2 parts, and to be honest, I am not sure I will get to cover both. So I prefer to explain in detail the first and not rush through both and not be able to just give you, you know, a rushy, incomplete version of the 2. So start with the first and let's see how far I get. If we don't have time, I think it's also the more interesting of the 2 parts. If I have the time, I will also talk about what is being done with obfuscation in location privacy. Okay, so obfuscation for private web search, I will talk about the model, I will talk about analysis and all the challenges that are posed by this kind of strategy. Okay, so what's the general idea in private web search? So the idea is that search queries are or might be very revealing and potentially very sensitive, okay? And this is a quote. We had a very nice symposium on obfuscation in New York, organized by Helen Nissenbaum and Seda Gurses. And one of the quotes that caught my attention by Helen was that she said, people should not be held accountable for their web searches. So it is, you know, it's not that because you are searching for certain information that, you know, you should be subject to consequences to that. It should be free for people to look for the information that they want to find. Who is the adversary here? The adversary is the search engine itself, okay? Either the search engine or any other entity with access to the search logs at the search engine. So what privacy technologies can we use to achieve private web search? So there are some really nice, fancy protocols that implement private search. These are, public key protocols, cryptographic protocols that allow you to send encrypted keywords to the search engine, that can do some processing in the encrypted domain, give you back results, and all of this in a way that the search engine does not learn the keywords, does not learn the results, and yet you still get like the documents that match the keywords that you were looking for. So this is all very nice, but the search engine has to actually implement the protocols. If they don't, then you don't have the service. And I'm not aware of any implementation of these protocols commercial for search. You could also use anonymous channels, so you could use Tor to access Google, and then your protection comes from anonymity. That's another alternative. But there's a third alternative, which is using an obfuscation tool. So the idea of an obfuscation tool is that you generate fake queries, dummy queries, that are automatically generated by some client software in your computer, and these queries introduce noise in the logs of the search engine. So when the search engine receives a query from you, it cannot tell whether it was you, the human, who sent the query, or if it was your computer that generated automatically. So essentially, what you're doing is hiding the real information, or the real queries, the user queries, in a pile of junk. Okay? And now, it should not be possible to see what is hay and what are needles in this pile of junk. If we compare these three strategies, crypto protocols have really nice, strong security guarantees. They are, expensive in terms of efficiency. Their main disadvantage is that they require the collaboration of the service provider. If you don't have that, so it's game over. Anonymity approaches. Security depends on the security of the anonymous channel, so you're relying on Tor, which is an external service, in order to achieve the privacy property. You pay in efficiency in the sense that your communications might be slower. What is nice is that you're not depending on the service provider doing anything to allow you to access their service. Although they might block Tor, although I'm not aware of Google, for example, blocking Tor. I don't think that's the case. It's not the case, actually. The third alternative, obfuscation, is very low efficiency cost for the user. I mean, you pay a little bit of bandwidth because you're sending some queries and getting some traffic back. But this is mostly an impact. The cost is mostly taken by the search engine itself, not by you. So in terms of sort of your own cost-benefit function, that you're good. You can implement it unilaterally. You do not depend on external services. You do not depend on the search engine, and the problem is that it's actually quite hard to achieve, solid privacy guarantees, as we will see. So what is the model of this service? Well, we might want to combine several techniques, but then I haven't seen any proposals of this, and analyzing the security of the composite system can be actually quite hard. Okay, so is this visible? Barely. Okay. So we have different parts in this model. So the first part is, okay, we have the user, that's the lady there, and she generates some queries, which are like this. Do you have a pointer? No. Okay. These little R's there, these packets, these are the real queries that are generated by the user. Okay. So queries by themselves, they are not so useful in terms of profiling, for example. What you would do, what the search engine would do, or the adversary would do, is to somehow use some form of semantic classification algorithm. This is the SCA there, semantic classification algorithm, to transform these queries into some form of profile. So if somebody is looking for, the World Cup, German team, all these things, then probably, you could categorize all these queries. Oh, that's wonderful. Green, beautiful. So, yeah, so this is the semantic classification algorithm. So the queries also, the user queries can also be represented as a profile. So this profile can say this person is interested in, in football, or in, mental diseases, or you name it. It depends on the sort of categories that you create. But you map queries to categories. So that's the user side. Now comes the tool, the actual obfuscation tool. Okay? The obfuscation tool is in the user computer. And this obfuscation tool will somehow take the queries generated by the user, and it outputs the queries of the user, unmodified in principle, although some tools do some little modifications, but most of them do not. And also some dummy queries, which are queries that are generated by the tool itself. So to generate those dummy queries, the tool needs to have some strategy. Strategy means, when do I generate the query? What sort of keywords do I use for this query? What sort of, maybe I also don't, maybe I want to use also some semantic classification algorithm, in the sense that it's not only which keywords do I use, but I choose these keywords in the as a function of the profile that I want to present. So maybe I choose them on certain topics. I want to appear as somebody who's very interested in football, therefore I'm going to generate queries that have keywords that are related to football. So, but for that, the tool has to have some awareness of the mapping between categories and keywords that go in the queries. Okay, so that's the tool. Is some plugin in your browser, for example. Then things go through the internet, and they get to the search engine, which is also the adversary in this model. Okay, so the adversary receives queries, Q, and a priori is not known whether these are from the user, so R queries or D queries, from the user or from the tool. Okay, so the user has his semantic classification algorithm, and on the one hand he has the queries, or the raw data in the queries, and on the other some representation of this data that is of interest to the adversary, because it classifies these queries into categories that are of interest. Because if I want to show you, advertising, a keyword in itself might not tell me much, but if I know that you are interested in this type of car, then I can show it to you, and maybe I get you to buy it, right? Okay, so we call this the naive adversary, because this naive adversary is just taking anything, any query it receives, and saying, okay, this is a query from this user. I'll just, build a profile from it. And this profile is what we call the observed profile. Okay. Now, a lot of tools that, actually, the work I'm talking about, this presentation is based on some work that we did, in which we analyzed 6 existing tools that use obfuscation to achieve private web search. And what was interesting was that nearly all of them stopped here. Okay, so they said, we propose this tool, we generate queries, and now we are going to see, these queries that are received and this profile that is constructed, and our tool works. We achieve privacy for some definition.
This doesn't eliminate any queries, though.
No, so far, no.
So for the naive adversary, it prevents a profile. No one can sell me potato chips because it's buried in questions about healthy food.
Yes.
But if it's, I don't know, if I'm searching for marijuana, then that search is still in there.
Yes.
And the DEA can.
Well, but maybe you can tell the DEA, it was the tool, it wasn't me.
That's an interesting one. I'll try that.
That's actually the point.
How smart are the queries? There was a few years ago. There was here a murder that the police found the suspect using his Google searches.
Wow.
He found how to wipe the knife out of DNA, and so how good would an obfuscation technique be? Would it create like tens of thousands more queries that it would be difficult for the police? Because like you said, the queries are still there.
Yes. Yeah, that's a very good point. So it really depends on the parameters, right? Like on the volume that you're generating, and on the dummy generation strategy, which is like the key issue. Like, how do you generate these queries in a way that they are plausible, in a way that they are really, difficult to distinguish?
But that's actually worse, because if the plausibility here is to write the query of how to wipe DNA off a knife, and you create dummy queries of how to wipe blood from a shirt, and how to wipe blood from anything else, and you increase the mass of
yes.
yes. Dummy queries about wiping blood.
Yes, absolutely. Yes, these are all great points, yes.
So I think more generally, so you have a distribution of X where you map queries to some topics. And then you have a distribution of Y. Are you trying to make it uniform over topics?
That's a possible strategy. That's a possible strategy.
You have this hard problem to decide on the mapping, how will you represent the world?
Yes.
Like making it uniform will solve all these problems.
Yes. Not even, I mean, it doesn't even have to be uniform. It could be any arbitrary shape that is, for example, if it's fixed, it would be the same, right? But these are all, you're raising really great points, everyone here, like seeing all the issues with obfuscation, even before I get to finish the model. That's really good. Okay, so what we did in our paper was basically add an additional stage of analysis, which is saying, okay, but the adversary is actually strategic, right? So if this adversary is strategic, and if we're doing security, and we are claiming, you know, that the system provides privacy in terms of as a security property, we need to have this strategic analysis. So what does this consist of? We say, okay, the adversary is doing some analysis. On the one hand, is looking at queries and trying to distinguish fake from real based on features. So, for example, some of the tools, or one of the tools was Track Me Not, and it was actually vulnerable to certain attacks looking at cookies and headers, because the cookie was only being sent with the dummy queries but not with the real queries. But since there is no anonymity, the IP address of origin is the same and the fingerprint of the device is also the same. So you could still link everything together and say, okay, these are the real queries, these are the fake queries. That was one. Another one was that the headers were only changed with the new real queries, because dummy queries were reusing headers. So these are all ways of distinguishing based on metadata, real and fake. There were also papers doing using machine learning, and I am not sure which features they were using, but I suspect they were using also content features, because the dummy queries might choose, choose keywords in a way that is not exactly the same way in which the human chooses the keywords. So especially if you have a large sample, you might be able to get to a point where you have some confidence in telling apart dummy and fake. So this is only looking at each query individually, okay? You can use all kinds of techniques, and it's very difficult to actually imitate a human. For example, imagine the queries, fake queries never have typos. Humans make typos. That could also give you hints of whether a query is real or fake. Or the queries, it's also the seeding. Where do you get these keywords from? Are you getting them from some RSS feed, for example? If you're getting them from a feed, then anything that is not in the feed must be real, because the tool would have never generated it. I'm actually jumping a little bit myself by giving you results, but just to illustrate like how one can do this dummy classification algorithm, can use different techniques to tell apart queries that are real and fake. And of course, you would have potentially fake, false positives, false negatives. It's probably not going to be perfect, but you would still be able to, with some confidence, already take out some of the noise. So that's at the query level. But there is also the profile level. So the adversary might not be satisfied with saying, okay, well, this is the profile I got with all these queries that have like junk in them. I actually want to have a clean profile. So for that, the adversary might be able to use some sort of profile filtering algorithm. And this comes into play because some of these obfuscation tools generated the dummy queries using a strategy that was aimed to increase or decrease certain categories. So this goes back to what you said about the uniform. So if I know, if it would be like uniform and I would say uniform, that would be very hard to do anything about it. But if I, for example, know that the tool is going to increase popular categories and sports is a very popular category, then I can say, okay, I will reduce the weight of sports in the filter profile with respect to the observed profile, because I know it has been artificially inflated. That's one example.
Usually when you get the results, you do something with them. You also decide about how
yeah.
to DNA from the knife. And then
yes, yes. That's a very good point too, that is usually not addressed by these tools. Absolutely. Like clicking, following up, absolutely. Yeah, that's another problem. Okay, and you could simulate random clicking to some extent, but still. Okay, so I think I said everything here. Yes. Okay, so we do this analysis in our paper. So what we did was we presented this model and say, okay, we're going to use this model now to analyze all these tools that have been proposed and then try to figure out like what sort of protection they offer and what sort of properties they provide, like evaluate their designs. So we distinguish between this query-based and profile-based analysis. So on the query level, the property that we look for is query indistinguishability. Okay, so dummy and real queries are indistinguishable. Why do we want this? Because we want plausible deniability. We want to say it was the tool who looked for marijuana, it was not me. Okay, and this should be plausible based on the evidence that is given. Okay, so you want plausible deniability properties. Yeah, that is not possible to tell apart. How would the attack try to distinguish? Exploit vulnerabilities in the dummy generation strategy that give this distinguishing characteristics. As I said, this can be metadata, this can be grammar of the queries, all kinds of things, seeding, all of these things. One issue that, because some of the queries of the systems try to address that, but one issue that is very difficult to address is query persistence in time, the topic persistence in time. So, I mean, sometimes when you're looking for some information, you maybe send a query and you get the response and you know everything you needed to know. But very often, you will need to make multiple queries, right? Or you will have some sort of topic that you're interested in because it's your topic of research or a topic of interest for you, and you would often go back to looking for information about that topic. So it is very difficult. So even if on a query-by-query basis, it is hard to distinguish whether it is real or fake, real queries are likely to have somehow a logic to them. That, that you look at the queries and you say, okay, this person looked for this, and then they looked for this, and then they looked for this. And I can see some reasoning that these are like, maybe the second query is a more specific query of something more general than they looked for in the beginning, or is related in some way to the same topic. So even if on a query-by-query basis you're good, taking sequences might give you away. And this is a little bit the problem with the long-term disclosure, right? That once you start considering multiple instances, you start having problems that you didn't have with single items. What about profile-based analysis? So the property that we seek here is profile obfuscation. We define profile obfuscation as the idea that given the observed profile, you should, even after you filter it, you should not gain information, or you should gain as little information as possible about the real profile, so the clean profile that only contains real queries. Okay. So this is, interestingly enough, this is not how people who propose systems that are operating mainly on the profile level, this is not how they thought about the privacy property. They thought about it typically in terms of similarity or dissimilarity. So a couple of the systems that we looked at, so one of them tried to say, okay, this is your real profile, and I'm going to represent this as a vector, in a multidimensional space, and this point in the space is your profile, which represents like the weight that you have for different categories. So what I'm going to do is try to find, with a budget of dummy queries, how I can minimize the cosine similarity. So try to take your observed profile as far away as possible, as fast as possible from what it is. Okay? So I would choose the dummy queries in a way that I move your profile as far away as possible. That's one strategy. The other strategy that other paper used was say, okay, this is sort of the average profile of the population, assuming we have that. And what we're going to try to do is to, if this is the middle point, the average point, and you're here, I'm also going to generate queries that bring you as fast as possible towards this average point. So this would be somehow a deterministic profile for everyone. Now, the problem with this, and then they would measure privacy based on how far you are from this middle point or how far you are from your real profile. Okay. Now, the problem with this is that because you are somehow moving in a space predictably, if I know that you're moving in the space and I know where you want to go and I know, what is the magnitude based on the budget that you have of dummies, I can somehow reverse that and see where you're coming from. Okay? So predictability of the modification of the profile is a big issue here. And what we argue is that you shouldn't look at how similar or different they are. You should look at how much information the end result, the end profile, is leaking about the original profile. So you can use for that, for example, mutual information. How correlated are they? Okay. Good. So another complication here is that we cannot just look at these two levels independently, because they interact with each other in weird ways that, to be honest, I don't think we understand completely. So if I am able to imagine probabilistically distinguish these queries, then obviously I'm able to somehow filter this profile, because the queries that contributed to a certain category, if I know they are dummy or if I suspect they are dummy, I can sort of reduce them, and this will modify the filtered profile that I obtain. But also the other way around. If I know that the strategy is profile-based and is trying to inflate certain categories by generating queries on those categories, then I not only can somehow lower the bars here of the categories that I know have been inflated, but then I can go back to the queries and say, okay, what queries actually contributed to this one? Then I will mark this as likely dummy, because, or more likely dummy, because I know the tool is trying to increase artificially this category. Okay. So if I can give you conclusions right now, saying that it is very hard to achieve a good, well-understood level of security with these techniques, which is very sad, because it's actually a very nice strategy that is very low cost. If it was effective, it would be really, really nice. And it might be effective to some extent in practice. The problem is that we cannot really formalize the effectiveness and have a sort of, as we'd like to have in security, have some sort of guarantees that hold. So challenges. First challenge is, to what extent can we predict the strategy of the adversary, or do we need to predict the strategy of the adversary? Okay. So there is this box that I didn't talk about too much, which is the semantic classification algorithm, which is this algorithm that transforms queries into categories. Okay. And the tool is making assumptions. What happens if the tool has a classification algorithm that is different from the one of the adversary? So a tool might be generating, have a very smart strategy to generate queries to modify your profile in a certain way, but it turns out that the adversary is using a completely different classification algorithm, and the modifications that you're obtaining are completely different. Or maybe, they become invalidated, and we have concrete examples in our case studies that show that once you change the semantic classification algorithm, you can start breaking down, the adversary might gain information that you were succeeding in hiding if you had used the same algorithm. So just to give you an example, so one example of obfuscation that is used actually by Helen in motivation of one of her papers is the use of chaff in World War II to conceal the position of a plane. So basically, a plane is flying and they throw like this little, papers cut to a certain wavelength, and this confuses the radar that then sees planes everywhere. I mean, this is only temporary because the papers eventually fall down. But while they are still in the air, tactically you get an advantage that it cannot locate where the plane is, it cannot shoot it down. Okay. Now, this works because you know what the wavelength of the radar is and how exactly you have to cut the papers for this to work. If you didn't know which wavelength to use, maybe you would be using papers that are actually not confused by the specific radar, and everything would not work. So in obfuscation, we actually have that kind of problem, because we don't really know what sort of tool the adversary is using. What about clicking links and downloading resources after that? That's also a big question. And the other question is, do we want the tool to be observable or unobservable? Do I want to tell the search engine I'm using this tool or not? So this is a very tricky one. If I tell the search engine I am using this tool. Maybe the search engine says, ah, yeah, so you're wasting my time. So now I'm going to, not serve you, or I'm going to delay responses to you. So you can be punished for using the tool, especially since it's a tool that considers the search engine as adversarial. So it's a bit of a conflict between the user and the service provider. And if we want it to be unobservable, then how can we guarantee that it's unobservable? Because then we have to, again, go into a security analysis that says we have this tool that generates queries, and not only it provides you with this protection, but also it cannot be detected that you're using it. But then, that's not so easy. Now, let's suppose that maybe that's the case, that you're able to make it unobservable. Do we want that? Because that's the same as having an adversary that behaves as naive instead of a strategic. So the adversary cannot filter out any queries. It takes everything it receives as the truth. Okay? And I mean, it might be an advantage, like Google. I don't think Google is implementing now, sophisticated data mining algorithms to filter out, like, for example, track me not queries, because the user base is not, I mean, even though it has had a lot of downloads, in the grand scheme of things, it's a small user base compared to the Google user base. So to what extent is it for them interesting to really invest in filtering out these queries? So are we succeeding then? Well, we still have a problem, because if the adversary takes the fake information as true, and now you have this profile that is modified with respect to your real profile, but the search engine believes that the profile is true, or considers that the profile is true, and treats it as if it was real, it will make decisions based on it. So what if this profile is even less advantageous for you than the one that you would have if you didn't have any noise? If, for example, if the concern that you have is that you will be price discriminated, maybe now with a new profile, you get even more expensive prices than if you didn't use the tool. So how do you, yeah?
So it depends on the motivation. So if you're worried about the police, yes, you don't want them to think that you're even worse than wrong. But if you're worried about somebody collecting business intelligence, for example, there's a company that I know that will not allow you to search the patent, Google patent website, because then they would know what kind of patents you're thinking about. So the fact that now there is no worse, you just don't want them to know what you're thinking. If they think you're thinking something else, you don't care what it is.
Yeah. It depends on it depends completely on the use case. I agree. Yeah. Yeah, I come back to that a little bit. But what I mean is that the problem here is that you're in a very asymmetric power relationship, in which the search engine is the one creating profiles and then using these profiles to make decisions that affect you. And the problem is that by modifying the profile, you modify those decisions, but you don't really have much control over in which way you modify them and whether these new decisions are going to be more advantageous to you than not using the tool. So to me, this is a big open question. Well, you get a different filter bubble, but you still get a filter bubble. That's the problem. It's not that you get out of it. You just get a different one. And maybe it's even a worse one. That's exactly the point. Then the issue is, like, do you include sensitive queries, yes or no? And this goes a little bit back to the marijuana, bloody knives, and all these things that have been brought up. Do you want to include that kind of query? So if you do not include it, you say, okay, no, the tool is not going to use, we have certain blacklists of keywords. We don't want to ask about drugs. We don't want to ask about illegal things. Okay? Then, okay, fair enough. But then anybody who's looking for a sensitive query, it's clear then that this sensitive query is true, because the tool would never generate it. So you lose on the deniability side in that sense. And then what is the usefulness of the tool? If you're self-censoring because you don't want to be held accountable for your searchers now, especially, particularly in those sensitive topics that you might need this the most, you are left unprotected. Now, if you include sensitive queries, then we go back to the first problem. What if these are considered as real? Then now is the burden of proof might be on you to prove that you're not, planning to kill anyone with a knife or whatever. Okay, so these are big challenges that I think go very much to the heart of the question. The problem here, again, is like the power relationship is that the one who holds the profile and makes decisions on it is going to do that regardless of whether the information is true or false. And it's difficult to escape from that. So what can we achieve? let's assume we can make a tool that really works, that provides you with deniability and profile obfuscation, and it works. So what can we achieve? So query deniability, that's something we can achieve. Okay, it was not me, it was the tool. Good. If many people would use the tool, this would be tantamount to having sort of a civil disobedience movement of saying, we are against profiling, we don't want this to happen, and we are sort of tampering with the system by generating all this junk, and we are enough people to make a difference and to make a point and to maybe put those that conduct this profiling on the spot, that they have to maybe rethink the way they are conducting business. But you would need many people to do this. If only a few people do it, that's not going to put enough pressure, right? If not many people use the tool, which is sort of the current situation, well, you might have a sense of satisfaction of saying, you think you know me, but you don't. So I think this is a little bit going to the patents. It's like, okay, you think you know what I'm up to, but actually you have no idea because, I'm doing something else. Now, you believe my business is going into this direction, but this is not the truth. So this actually is something that is achievable even if not many people use it, even if you are the only one who uses it, really. You would also prevent maybe manipulations that are like, if I am, let's assume that profiling is so good that I can sort of guess what makes you tick exactly. So I know that you're like a compulsive buyer, and that if I show you like a picture of a kitty, then you will buy anything that is next to the cat. But actually you don't like cats. In reality, that's only your fake profile. Your real profile is that you like elephants. But I'm not showing you elephants, therefore I cannot sort of manipulate you into buying my product. So that could work. Yeah, and one thing to keep in mind is that even if the dummy queries are generated, and this is going back to the point that you mentioned before, is that the real queries are still there. Okay, so if we think of cases such as the American Online case, in which people were de-anonymized based on their queries, this would still be possible, because the real queries that led to her de-anonymization would not have been removed or modified. They would be added with other things that maybe introduce some confusion for the people trying to identify the person, but still would not prevent this kind of threat. Okay, so possible ways forward if we want to think about what to do with these kind of tools. So one idea would be to let users indicate the type of profile they would like to present to the search engine, and then tailor the dummy generation strategy to achieve that profile. So you can say, I want to appear as somebody who is, a very careful buyer who looks at many options before making a decision, because I know that this is the way I will get, a better deal than if I appear as a compulsive buyer. I will get the first thing they're shown. So if you have, but for that you need to have, again, information about how decisions are being made of profiles, to say, I want to be the guy who has this profile because this is the profile that, I feel comfortable with, or the profile that will give me, advantages. If you don't have access to the logic of the profiling and the decision making, you're a bit it's hard. You could use it as a tool for solidarity. So imagine that you say, there is discrimination against people who look for, who make breast cancer or AIDS queries. There's a big stigma. And what we do is that we precisely use the tool to have like a list of sensitive queries that we want to provide cover and support for, so that anybody looking for AIDS can do so, and it would look like it's fake because there are all these people generating junk queries about AIDS, for example. So to sort of take out the stigma of maybe certain queries that are sensitive, but that people feel solidarity with those who want to do those searches and want to provide sort of cover for them. And then, of course, we could also combine this with anonymity, and then we would use, obtain maybe benefits from both sides of both types of technologies. And this is really my last slide about this. And I think, yeah, we are out of time. I will jump to the conclusions of the thing. Advantages of obfuscation: unilaterally, you can deploy it. You don't need to engage the service providers. It's very simple and it's very low cost in many cases. Disadvantages: it's not really secure. the protection is very weak and it's hard to analyze. Like having like a proper analysis that even if we say it's weak, it's hard for us to say how weak because it's difficult to make an analysis that really gives you a good idea of how much security you're getting with one strategy or with another strategy. And it's really a very open question, I think, whether these strategies are viable and what we can achieve with them. So, yeah.
If many people use these tools, it's going to create a huge amount of junk traffic
Yes.
and explode the search engines.
Yeah.
Is there anything you have to say about this? Like, if currently it's mainly research in small number of people, so it's not that bad. But if everyone uses it as standard, like the search engines are going to have to multiply their resources by, I don't know, tenfold or more.
Yeah, I think part of the idea behind these tools is to precisely sort of protest. Is that so? Helen Nissenbaum calls the obfuscation tools as the weapon of the weak. So it's a way of protesting against certain practices that you really don't have the power to contest in other ways. So it would be a way to at least if you would show force from the user base in that way, at least it would be a way to maybe bring those entities to the negotiation table and say, okay, how can we do things in a way that everybody feels more comfortable instead of the search engine unilaterally deciding, what sort of information they're going to collect and how they're going to use it.
Is there a way to do this kind of obfuscation without creating junk traffic? Maybe redirect the queries in different ways so it doesn't seem like it's the
well,
user.
Then you would go into anonymity approaches, right? I guess what I'm saying is that increasing this load, I think it's in a way part of the strategy, actually. I think it's actually intentional in some ways,
Question might actually relate a little bit. Throughout the talk, you've been talking about privacy, but outside the search engine. The search engine is like beyond. And the question is, can you maybe put it inside the search engine in a certain sense? I'm sure Google searches won't allow this, but maybe in some sense we can do it naively outside. So we have different questions going in that can kind of blur out your real question, and then outside, when we have some of the data, do some simple additional search analysis, like do the last step of the search outside the search engine. And that way sort of bring the privacy into the search area.
So I think that these tools do that to some extent, because what they do is that they send all these questions and then you filter at the client side the questions that are not relevant, and you only give to the user.
So the question is you don't ask the actual query that you want plus dummy questions, but you ask partial. So I will ask about marijuana education, and then someone else would ask
about combustion of.
So I get these very naive questions being asked. The idea that the engine itself never sees the actual query, and then the last part of the query where you really want to ask the actual query, you combine it outside the search engine. That kind of hides it from the search people themselves. And
so I'm not expert on search, but I'm not sure to what extent this is compatible with how search algorithms work, in the sense that you might get, if you look for marijuana education, you might get a set of results that do not contain as a subset the ones that you're interested in.
Have to come into the loop.
So you create a search engine.
Are these tools static? Do they adjust with time? Like you can do it dynamic, and then maybe you can somehow hide the predictions.
Yeah. So a lot of the tools, they do evolve in some way. Like some of them would, like for example, obtain new keywords from pages that are downloaded, or have like seeding keywords that are also not a static list, but that changes.
To the user, or
Sorry?
are they adaptive to the user, or there's just
So I don't think Track Me Not is adaptive to the user. I don't know if they take keywords, for example, for the pages you download. I know some of the other academic proposals did evolve to some extent with the user behavior, but it was the proposal, and it was not clear how that would work in practice, because it was really just like an algorithm for this increasing this cosine dissimilarity, and they didn't, I mean, I think, yeah, you need to implement it and have real users in order to see how that works. Only TrackMeNot really has, we looked at 6 proposals, but the only one that really has a user base and an implementation that works and all of that is TrackMeNot. The others are just a paper. Maybe they have prototypes, but we haven't really seen the software. Is that it? Questions? It's one. Okay, thank you very much.